and we'll be able to get some interesting results. It ended up being not so simple. So here is the tool. Ours is fairly simple. I believe Asif would talk about maybe more complicated, or more advanced setups later. So here is the instrument that we have in IIT Bombay. It's High-throughput nano indenter. This is the transducer, which I feel is the heart of the instrument, which allows you to impose loads, displacements, measure loads and displacements. And to the transducer is attached a tip, which is typically diamond. And the tip that we use more often for our indentations is a three-sided pyramid, and it's referred to as a Berkovich tip, which has a well-known semi-angle of about 65 degrees, which has an included angle of about 142 degrees. And when we started out, the goal was very simple. We wanted to measure the hardness and modulus. And we thought that as we vary the extent of cross-linking in this material, we should see differences in hardness and modulus. Let's see what we see. So, but let me first digress a little bit. Where would you use something like this? Where would you use a tool like this? And there are two places where one would want to use a tool like this. One is where your samples themselves are small. So this is an example from a work that we had done where we took zirconium, actually, bulk zirconium, high purity, and we machined out small pillar samples out of it. And our curiosity was that what happens. So you see these colors, they indicate orientations as per this color scale right here. And here, what the pink strip that you see in between the two large green regions is a twin. And at this point, I won't go into details of what a twin is. Several of you may already know. It's a special kind of a boundary. So we were curious to see, can we experimentally measure differences in mechanical response brought about by the presence of a boundary? So we made samples, these tiny pillar samples, we made them in single crystal regions. So within this grain and within this grain, and we deliberately made them at the boundary, incorporating exactly one boundary. And we deformed them and we looked at their mechanical response, and we got to learn some things about what boundaries do. So that could be one place. You have small samples and you want to test them. The other place where you might want to use them is where your samples are bulk. This is now a nickel-based superalloy, which has been used to make a directionally solidified blade for a turbine. And this is a bulk material with fairly large grains. But of course, when you start looking at it closely, it has a complex microstructure. So here you see, what you see as dark gray and light gray are the gamma and gamma prime phases. Again, this is not a talk about phases and so on. This line that you see here is a grain boundary. Excuse me. And at the boundary, you see things like these bright things, which are precipitates. And it is this very complex microstructure, excuse me, which gives these blades their high temperature strength. Right? So now you may want to know exactly how strong this carbide is. You may want to know how the strength of this carbide changes as a function of temperature, because you want this blade to function very well at 700, 750, 800 degrees C. So you would need a tool that would allow you to indent this carbide and no other place and probe the mechanical properties, right? And this is, I see that Richa joined the talk at just the right time. So, and this is a higher level magnification image of this region, that there are even finer features which you may or may not be able to probe using nanoindentation. Okay. So the other place where you want to use it is where your sample is bulk, but it has fine microstructural features, and you want to probe those individual microstructural features and not get interference from other things. Okay. The last example I have is again from bulk. We've been looking at copper and copper aluminum alloys. These are very nice systems because as you add aluminum, an inherent property of the material called stacking fault energy changes. And that has interesting implications in deformation. So now what we've done is, this is an example of the alloy. Again, it's a bulk sample. we actually make these tensile test samples out of it and we deform it. And we identify a certain region, which is shown here by this red oval. And we look at that region after multiple steps of deformation, the exact same region. Again, I'm interested in what happens near boundaries. Okay, so this is one image. The colors again correspond to orientations that you see here. And what you see, so this is the undeformed sample. These very beautiful straight lines are boundaries. Some of them are grain boundaries. Some of them are what are called CSL twin boundaries. And we deform it. This is after 0.2 strain. This is after 0.3 strain. And the shades that you see in colors basically indicate that the local orientation is changing. The lattice is getting distorted. And this lattice distortion, one could be that I just want to understand the origins of this lattice distortion. Maybe I would like to model it. The other is I again may want to probe the changes in hardness that happen when I go from, say, here, a heavily distorted region, to here, maybe which is not so distorted. Okay, so you once again need a probe which is very small, which can let you see differences between hardness here versus hardness here. So you would use, something like a nano indenter, which has a very small tip, allows you to impose loads in a fairly controlled manner and measure displacements at fairly good resolutions. So these are all, as you can see, these are metals and alloys, right? My first love, the thing that I was trained to understand. But then again, we ventured into SU8, and before I land up to SU8, I'm going to give you a very brief, basic introduction to nano indentation. Again, plain vanilla nano indentation, not advanced techniques, which will come later as the day goes along, but very simple nano indentation, conventional, right? So this is the experiment that you do. You can impose a load. You can control how quickly that load is applied, in what amount of time. You can then hold at that maximum load or not hold at that maximum load as you feel like, and then you unload. This is the input that you give. If you're doing a load control experiment, if you're doing a displacement control experiment, then your control becomes displacement and the measured quantity becomes load. In this schematic, load is what I'm controlling as a function of time, and this black curve shows displacement, which I'm measuring. So if I impose this load, what sort of a displacement do I get? So that's my experimental input. Okay. Now, there are modes that I can control. I already mentioned load and displacement control, and then there are loading conditions that I can further control. So I could control the rate of loading or the rate of displacement, or I could control what is called the normalized loading rate, P dot by P or H dot by H. And you'll see that all of our experiments are done in this mode because this translates into a constant strain rate, which would be familiar to you, those of you who are used to doing mechanical testing. Typically, we do our mechanical test in a strain rate controlled manner. Its equivalent in nano indentation is this P dot by P control. So we do those experiments, and then this is the data that you get. Again, load shown as a function of displacement or depth of penetration into the sample, right? So the load increases, displacement increases. Again, there's a tiny hole here which you cannot see, and then we unload and we land up at some point. So there are a few quantities here. Once again, apologies to experts, but in the interest of students, I'll spell these out. So there is the maximum load that is applied, P maximum, the maximum depth to which the probe goes into the sample, that is H max. And then when I unload, of course, now the sample is indented, right? So it doesn't come back to the surface. There is some final or residual depth to which I come back. Now here is a schematic of the same, and I want to highlight a few other things here. Sorry, this black box keeps coming. Okay, so this is my sample surface. The tip comes into contact during loading, goes in. This is this loading part. I've reached maximum load. Now at maximum load, I want to point out a few more terms. I had said there is a maximum depth to which the tip has gone in, H max, right? Now that maximum depth, we have separated it into two components, if you can see this part. So there is HC, where C stands for contact, the contact depth. And there is HS, which is essentially sink in. And if you look carefully at the schematic here, what you notice is that the sink-in depth is where the surface profile is curving inward, but that part is not in contact with the tip. It is only this part corresponding to a depth HC, which is in contact with the surface of the tip. So you will see that this plays a very important role in our analysis, and I'll come to it in the very next slide. And then we unload. And this is the final depth to which we've ended up in after the tip has been retracted. So that's my H final, which is shown right here. Okay. So now let's look at this HC a little bit more. What happened? Huh. Well, my slide refuses. There we go. Okay. So now, fine. We've got this. We've done our experiment. We've got the data. What do we measure? I said we are interested in two quantities, hardness and modulus. Okay, hardness is relatively simple, that if I know the maximum load that I've applied and I can figure out a contact area, I'll show you in a second what I mean by contact area, then hardness is the maximum load divided by the contact area. Okay, sort of like pressure. And reduced modulus, this was actually this equation. It's a function of a quantity called stiffness and contact area, and we'll define it in just a little bit. This actually comes from a contact mechanics analysis by Snedden, who gave his analysis for an elastic sphere indenting an infinite half space. Okay, and the very large contribution that Oliver and Farr and co-workers made was that they took Snedden's analysis, which was done for a very specialized case, and they showed that, look, you actually can use it even when you're not indenting in the infinite elastic half space, and even when your indenter is not a sphere. And that was this paper, and that really opened up this area. No, so remarkable contribution. So what is this contact area? Well, that contact area is this. Remember, I identified a contact depth in the previous slide. The depth which is actually in contact with the tip when maximum load is applied to the tip. So if I know this depth, and early on I had told you that, well, I know the geometry of my tip, right? I bought this tip. It's a precisely machined diamond tip. I know the included angle. So if I could measure this depth, this is class 10 geometry, you could calculate this contact area very simply, right? So now I need to know what this contact depth is. My instrument has only measured the maximum depth to which my tip has gone in. So, and this was again shown by Oliver and Farr and co-workers that, look, this, so what I need to do is my maximum depth is comprised of this contact depth and sink-in depth. So if I could just subtract this sink-in depth from the maximum depth, then I have my contact depth, and then I have this area, and at least hardness calculation is done. And they showed that, look, the sink-in depth, you can actually calculate it using a relation of this type. Again, I'm not going into details of this relation because these derivations are fairly well spelled out now in various books. This number you have to be a little careful about. This number is a function of the kind of tip that you are using. And what we have found out is that tips are never perfect to begin with, and they blunt with usage. So there is a possibility that this number changes. So again, graduate students among you who are using this extensively for research should be a little careful about blindly using this relationship. Okay. So P max is again my maximum load. H max I got from my experiment. So now I just need this and I'm home. So what is this S? It's a stiffness. Okay. And this stiffness is dP by dH. It's the slope of my unloading curve. So I have my unloading curve. If I could get the slope of the unloading curve, then again, I'm done, right? So how do I go about getting the slope of the unloading curve? I'll come to that, the slope of the unloading curve, but let me dwell a little bit on this contact area first. Okay, I said, well, if you know HC, you can calculate AC, right? If you know, and how would you do that? Well, if your tip were perfect, forget about this thing in the red box right now, but if your tip was perfect, then first, area of contact would simply be given by √3/4a square. Okay. And because this is an equilateral triangle, you know the area of an equilateral triangle, and A in terms of HC would simply be given by this 3 square root 3 tan square of that included angle into HC square. Of course, Oliver and Farr also acknowledged that tips are not perfect, tips are blunt, and they proposed that, look, to this geometric relationship, which holds true for a perfectly sharp tip, you add these correction factors. They said, well, let's take an 8th order polynomial, and you figure out what these correction factors are by indenting on a known material, which in most cases is quartz. And by fitting, you figure out what these correction factors are. And once you've done the fit, then you know the correction for tip bluntness, and now you can use it for any unknown material. So life is fairly simple. Not so, we found out. So, okay, so this is the last bit. How do I get S? Well, you get S by fitting this unloading curve to a power law. So again, this was Oliver and Farr's contribution that prior to them, Nix and colleagues had said that, well, this is the initial part of this unloading curve is pretty much linear. You can fit a straight line to it. That's the dotted straight line here. And from that fit, you can obtain the slope of the, you take the slope of that straight line, and that's your S. What Oliver and Farr said that, well, look, this is obviously not a straight line if you look at this curve. So let's not force it to fit a straight line. It actually better fits a power law. And they showed that for a range of materials, ceramics, metals, this and that, power law is a good fit. So you fit a power law to it. And here A and HF and M are all fitting parameters. So you take some part of this data, you fit a power law equation to it. And once you have your power law equation, you can calculate dP by dH, right? You differentiate this. And once you differentiate this, you realize it can very simply be written like this: M into P into H minus HF. Okay. So the only variables that you're getting from the fit are this power law coefficient M and HF. And then you evaluate this at P is equal to P max, which also you've got from your experiment. So that's it. You are all set. We thought we were all set. We understand this method. It's been used a lot. It's been shown to work for a range of materials. We know everything. The student will do the experiments. We'll analyze the data and we'll be done. Home. That was a few years ago. Okay. We also, just to be a thorough, we trained the student. We said, like, look, fits may look very nice like this, but it is not until you look at the residuals that you realize whether fits are good or not. And I'm going to revisit this idea of looking at residuals to evaluate how good your fits are in a little bit. Okay. So now my understanding is in place. Here is the material that I'm going to indent. It's an epoxy polymer. It's called SU8. This is the monomer that is used. Don't even ask me to pronounce the full name of this. Not a chemist. But what it has is, it has these 8 benzene rings. Okay, and it has this epoxy group at the end of each of these arms. And to cross-link it, I'll show you the process in a second. To cross-link it, what we essentially have to do is open up these epoxies. And then each of these can cross-link with another of the monomers, essentially giving it an 8-fold functionality. Okay, so all of these are available for cross-linking. And fabrication is very convenient. The reason we chose SU8 was that we have a clean room here. People there routinely use SU8 as a photoresist. It was available in high purity. We could easily make samples. So we said, okay, fine, let's do SU8. Okay. So this is the process that we use. That we basically put a dollop of this monomer on a silicon wafer. We spin that silicon wafer to spread the monomer as a film. And then we heat it. So heating is a multi-stage process. So we heat it, and then we expose it to UV radiation. And the UV radiation basically catalyzes the opening up of that epoxy ring. Okay, so it releases the photocatalyst, which opens up that ring. And then we heat it again, essentially to speed up the cross-linking reaction. So that's the net process. And by controlling, UV process, we don't have much control over, but controlling either this preheating temperature or the post bake temperature, we can control the extent of cross-linking. And that's what we did. Okay, so there is not the preheating, sorry, only the post-bake. So you see there are these two levels of baking. So this temperature and time, and this temperature and time. This I definitely need to do because I need to get rid of the solvent before I do this UV exposure. So we do this. We do the post-exposure bake at 90 degrees, and we do a hard bake at 150 degrees. These are the two steps 4 and 5 from the previous one. And this is the variation that we have done. So post-bake for 5 minutes, for 30 minutes. In some cases, the post-bake for 30 minutes followed by hard bake for 15 minutes, and post-bake for 30 minutes followed by hard bake for 30 minutes. This is expected to be the most cross-linked sample. This is expected to be the least cross-linked sample. Okay. And then we did measure the level of cross-linking using an FTIR system. And we also realized in doing this that the temperature at which you do your FTIR measurement makes a difference. So we did it at the baking temperatures, 95 degrees and 150 degrees. And then we indented those samples. They're all done in this constant P dot by P mode. We went to this particular maximum load, and this is the load cycle that we followed. So this is standard information. So these are our FTIR results. That you're basically what you're looking for is that the epoxy is going to open up and cross-link, right? So as more and more cross-linking happens, that epoxy peak is going to go down in intensity, whereas nothing is going to happen to your benzene rings. So you normalize the intensity of your epoxy peaks with that of the benzene, and that gives you a measure of the extent of cross-linking that has happened. Okay, so that's what we did. And we found that the black here is the cross-linked segments, which is here. So we are going in PB5. We've got about 82% cross-linked, whereas in your HB30, the most heated sample, we are up at about 96-97% cross-linking. What is interesting is that instead of thinking in terms of these 82% of this thing, you think about the amount left uncross-linked. Okay, so there's only 4% left uncross-linked here, and there's about 18% left uncross-linked here in this sample. Okay, and we did nano indentation. So same figure, and we did our area of contact calculation. We could calculate the sink in, we could fit the S. I'll come to this low S in a second. Don't worry about that right now. Sink in, and this was a previous student, Sandeepan, who had done this work. And we calculated our stiffnesses and our contact areas, and this is the point at which we started to get a little concerned. So here is the stiffness slope of the unloading curve, and this is counterintuitive. We had expected that higher the level of cross-linking, the stiffer will be the sample. But that's not what we are finding. Okay, we are finding that these have a higher contact area. The more cross-linked samples have a higher contact area. We are calculating a higher contact area, not have. And we are measuring lower stiffnesses for them. Now, this combination of a lower stiffness and a higher contact area, of course, gives us a lower modulus for the more cross-linked sample. and a lower hardness. Now, at this point, we said, well, this is not making sense. And this is where, Sandeepan had more or less was finishing his work, and this new student, Prakash, was coming in. And I'll basically be talking about his work from this point onwards. Right, so you can see this right here, that if this is low and this is high, then I get a lower reduced modulus. And we spent a lot of time worrying about what could go wrong, right? I'll show you a listing. Sorry, at some point, my screen just gets a little stuck. Yeah. So this is Prakash scratching his head. That what happened. So we said, okay, we listed the various possible reasons, and there were some which were very easy to validate. We said, well, okay, maybe there's thickness variation, maybe there's roughness variation. You didn't make your sample properly. Maybe there's thermal drift, and I will talk about thermal drift in the next few slides because I think it's important for people to keep that in mind. Then we said, okay, maybe the sample which is more cross-linked has actually also become more brittle. So maybe there's subsurface cracking which we can't see, and that's making it effectively more compliant. Or maybe there are pileups in the softer sample, right, which are giving complications. So we set about confirming or denying them, and the thickness was okay, roughness was low, drift rate in this case was low, but like I said, I would still like to talk about this. And the total time of the experiment was within this linear limit, which I'll talk about. There were no pop-ins in our experiments, which are indicative of displacement bursts when a crack happens. And there were no pileups. We imaged our samples very carefully. There were no pileups. So we said, okay, the easy reasons are ruled out. But let me just take you on a slight detour for this thermal drift, because again, if there are students here, you should think about it. Okay. Those of you who do nano indentation know that the instrument itself takes into account that there would be drift. Drift basically means that the tip is going to move without you wanting it to move, right? And it's not an imposed displacement or not an imposed load. It's just going to move on its own. And that movement or that displacement needs to be corrected from the total displacement. Otherwise, it'll give you erroneous results. So at the beginning of every experiment, this is automatically done, right? Displacement is measured as a function of time for 40 seconds, and the last 20 seconds to the last 20 seconds of data, a straight line is fit, m into t plus c kind of a straight line. This m is calculated, right? And then if you know the time of your experiment, then you know the slope, you calculate displacement due to drift, you subtract it from the total data, and you know the displacement into the sample, the intended displacement. So that's fairly straightforward, right? So here is experimental data from quartz, which is not viscoelastic. So we can't blame viscoelasticity for any of these results. The experiment is done in a P dot by P controlled mode, 0.1 seconds in both the cases. The only difference is the red curve. We load it up to 10,000 micronewton, 10 millinewton. We hold it for 10 seconds and we unload it in 20 seconds. Here we hold it for 100 seconds and we unload it in 20 seconds. And you can clearly see this black curve is not making a lot of sense. Right now, the reason I'm showing you this example from quartz is that because we say, okay, quartz is not viscoelastic, and room temperature experiment, the labs are usually kept cold to a temperature of about 22, 23 degrees. I'm not going to have to worry about drift, but you do, and you should check. So we've done a lot of studies on drift correction, and this is again these displacement measurements with no applied load, and this is drift monitoring time. Okay, and this black here is 100 seconds, the blue is 120 seconds, and the green is 140 seconds, and the black are straight lines fitted to that, right? Mx plus c. And you can see the black and blue, the green you can't see very clearly. I'm sorry about that. But here you can see the straight line fit is fine. So my original drift data that I've collected, that should work. I subtract that and I should get sensible results. But here you see these pluses are 180 seconds. And you see that the straight line fit is useless. Here is 160 seconds, here is 200 seconds. The straight line fit means nothing. So I need another scheme for drift correction. And in a previous paper, we proposed a quadratic drift correction, which is not what I'm going to talk about this time. I'm going to propose a much simpler relation. So when Prakash had written in his earlier slide that his experiments were within this linear, this thing, we found that 1/42, it's still linear. So if your experiment, either you give a load function so that your experiment finishes in 140 seconds, in which case you're fine, or you basically do drift monitoring for the duration of your experiment. Just collect displacement data as a function of time, and then subtract that from your measured data. And if you do that, here are the red and the black curves again, the same data as the previous slide, and everything looks fine now. Okay, so that's a very simple way of doing drift correction, and you should think about it if you're doing long duration experiments. As per our measurements, anything more than 140 seconds. Okay, so the easy reasons have been ruled out. Now come the more complicated reasons. We know that our material is viscoelastic. We were also worried that is there some adhesion. We were wondering whether, varying the crosslink density also does something to adhesion at the surface. And we were wondering, are we making errors in calculation of the area of contact, right? Because that goes into my equation. And is that the source of error? So viscoelasticity first, that's the easiest to deal with. This is the starting H instantaneous and versus the starting depth at the beginning of the hold segment, right? So this is that holding segment that I gave. And you can see that displacement is still increasing, right? So a 4-second hold, a 5-second hold doesn't do it for me. But if I give a long holding time here, if I hold it for about 70 seconds, you can see that this has plateaued out, right? So if I give a long enough holding time and then unload, then I hope to have gotten rid of effects of viscoelastic deformation, confounding my unloading results. So we said, okay, fine, we can give a long hold time. But again, you should be aware that if I give a long hold time, my duration of experiment goes up, and I have another limit that if I do long experiments, there is drift. So you have to take care of all of these issues. So viscoelasticity was easy. We also measured adhesion. And I think Pratyank and Asif helped us figure out how to measure adhesion. So we basically, this is the load versus time. This is the load function that we gave. We load up the sample, we hold it for a longish time, and then we very quickly unload, just yank it out as fast as we can. And we are doing this in, we turn off the feedback, because otherwise it's going to try to bring the load back to 0 and stop there. So when we turn off feedback, then it goes down to this point, to a negative load, which basically means the tip is kind of being sucked by the surface, and we have to pull against that. And then it tries to bring it back to 0 by pulling it against the adhesion. And this peak is what we measure as adhesion during unloading. So you can see these pull-off loads. They are a function of how fast we are unloading. So I want you to just focus on the fastest unload that we could do, 5,000 micronewton per second. And the pull-off force is about 8 micronewton. It's not huge, but it's there. And it's not varying a whole lot by the amount of cross-linking. Okay, but we said, okay, there is adhesion. Maybe it can complicate things, especially when we are loading the sample, because then we are literally pushing the two surfaces together. So we did decide to gold coat the samples to get rid of adhesion effects, a very thin layer, just enough to get rid of it. And here is a pictorial view of what adhesion does, right? So this is an SPM image of the indent, and you can see these spikes. I think there's a better figure in the next slide, but you look at this surface, which is in SU8, the PB5 sample, and look at this in quartz. It's so smooth after unloading, right? So we believe that all of these jagged edges that we are seeing is because of pulling off the tip from a surface which is sticking to it, and that could complicate your results. So here is a side view. And what we feel is happening is the tip went in till here. And as we pull it back up, there is all this pulling that happens. And when we finally yank it out, this would have been the profile of the tip when it was all the way in, and all of this convolution that is happening is because the surface is getting pulled up a little bit when we pull the tip out. Okay, so I'm not going to go into details of this. It doesn't have any bearing on the story that I'm telling you today, but again, factors that do play a role, that will play a role and may, depending on what you are after, need looking into. Now, this calculation of area of contact, okay, could there be problems in fitting, right? Because if you remember, the area of contact is a function of contact depth, right? The equation that Oliver and Farr had given us. And my contact depth, I'm getting from this, right? I measure in S and then I subtract this epsilon, some 0.75 into P max by S from my H max to get my depth of contact. So if I'm making mistakes here, it'll reflect in my other calculations. So this is the unloading curve. This is now data from SU8. And you look at this fit, and if I just look at it, it looks kind of okay. But now you plot the residuals and they look really bad. So again, you need to look at the residuals and then take a call as to what you need to do, right? So you take some fraction of your unloading data, and if you have smooth data, you might be able to just fit to it and get randomly distributed residuals distributed randomly about 0 and reasonably small. And you fit it and you're good to go, calculate your S. But you might have noisy data for various reasons, in which case you might want to explore smoothing that data first with a smoothing function. We've looked at a few. LOS is one. There is some other algorithm, some Chavesky-Golay, which we have used, which gives reasonable results. So some processing may be done and then fitted with a suitable equation, I'm saying, because the original proposal was power law. Okay. But if you're still running into errors, you may want to explore, say, polynomial fitting. There's nothing very sacrosanct about power law. So here I'm showing you data from quartz. Okay, quartz, which is not viscoelastic, which does not have adhesion issues. And here is the contact area measurement, right? So, and this, we know the modulus of quartz reasonably well. Contact area goes as pi over 4 S square over E square. The squares are my experimental data points. This is my fitting curve and everything works well. This is my contact area that I've been able to get from this sort of an equation. Okay. But it doesn't quite work that well for SU8. Okay. I do the same process, which I know works for quartz. And what I find is that we took an indent. In fact, we took several indents. Prakash took several indents and he imaged them, both using SPM, which is using the same tip to image the indent that he had used to create the indent in the first place, and using AFM. And we measured this length A, right? That's this length of the triangle, the residual triangle. And that's our equation, right? That is how I'm supposed to calculate the contact area. And what we found is that if I use this measured length A, the contact area that I calculate like this using the geometry is actually greater than the area that I was earlier calculating using the contact depth that I had got from my previous measurements. So there is some problem in taking the standard method and applying it to it. These two don't match up. Okay, that's what it took us a while to get to. So here is the same figure again, that the actual contact area is greater than AC. And that turned out to be the source of our troubles. Okay, so if you, and then Prakash did these measurements for several indents in samples with various levels of cross-linking. And instead of using the standard method, we simply said, look, once we've measured this A, this is the contact area. I can calculate the contact area directly like this, and I can calculate the ER and the H. And if I do that, then these are the values that I get. My less cross-linked sample is indeed has a less modulus. My more cross-linked sample indeed has a higher modulus, and the same goes for hardness. And the difference is definitely not negligible. Okay. So okay. And why was this happening? The reason this was happening is, of course, because our this correction that we end up using, right? This correction that we end up using, this correction was not working quite well for our system. So we did an estimation of the blunt depth. Now, to explain to you what a blunt depth is, you remember I said a perfect tip, right, is not, or rather we assume that it's a perfect tip. Let me see whether it's going to let me write on this at all. Right? So we are assuming, I'm going to make a 2D drawing. I'm assuming my tip is like this. And I know the included angles, but you see my tip is not like this. And it is to take care, my tip is actually something like this. And Oliver and Farr had proposed that, look, you take this 8th order polynomial and you fit to it, and it takes care of this blunting for you. And what we found is that that may not be working. So we have estimated what we are calling the blunt depth, which is basically this depth. This depth. We've estimated it from our measurements. Again, that's a topic of a whole separate talk. But we've estimated it, and we've estimated it for a function, as a function of time, because the tip gets used. Where we work is a central facility. Lots of people use it for lots of reasons. So you see, as a function of time, and you can focus on just this last column. Okay, don't worry about the multiple numbers. This depth goes from 10 nanometers to 28 nanometers in a space of about 600 days. So it's over a 50% change, but it is occurring over a period of about 2 years. Please note this includes lockdown, so this is an underestimate. And then we were also brave enough, so this is the same thing shown as a plot, and Prakash was also brave enough to then take the tip into an SEM. And I don't know whether you can see this very clearly, and it doesn't allow me to zoom in, but right here is where he's been able to estimate this blunt depth from his SEM image. And if you see that, that it came out to be about 27 nanometers. So at about 530 days, we had estimated about 25 nanometer. This is 27. In 600 days, we were at about 27, 28. So we think what we are doing is sensible. And so either you're able to correct for this in a manner which is better than the current recipe, or you just go ahead and measure this area of contact and do a calculation of your hardness and modulus. This works for us, calculation of the hardness and modulus. Yeah, sorry, I thought I had a slide on recovery, but I also think I've pretty much reached the end of my speaking time. So I think I'm gonna stop here. Yeah, I don't have the recovery slide, so I'll leave that. So I'm just going to summarize the results that so you can make these samples, you can pick a system which works easily for you, you can play with cross-linking density. It is good to know the conventional methods very well. It is also good to look at your data and think about it very critically. We could get rid of adhesion, we could get rid of viscoelasticity, and then we had to focus on the calculation of area of contact itself. And once we did that, we are able to accurately calculate the changes in modulus and hardness that occur as a function of cross-linking. Okay, so the modulus goes up, the hardness goes up as the extent of cross-linking goes up. So with that, I'm going to stop. This is a picture of our campus. I think this is the building where I live, from where I'm giving my talk right now. This is Powai Lake, and my department is somewhere here in this cluster, I think. Yeah, the rest are student hostels. So thank you very much for listening. And I would be very happy to answer your questions or take any comments that you have.
Sure, it was pretty good talk and thought-provoking. I'm sure the students will also get benefit out of it. We got one question from Himanshu here. He was asking whether the surface roughness at nanoscale was taken into account while measuring the same. So
Sorry,
surface.
Pratyank, can you repeat? I was just increasing the volume on my setup.
Okay, sure. He's asking whether the
Yeah.
surface roughness at nanoscale was taken into account while measuring the same.
We measured the surface roughness and it was very small, negligible. So it's not the effect of surface roughness, but we did measure it. Yes. I think it came out to be about 2 nanometers.
Okay, that's
Yeah.
pretty, yeah, pretty smooth.
Yeah. Yeah. It's pretty flat. It's pretty flat.
Pretty flat. Sure.
Yeah. It's here.
Yeah,
Yeah. It's about 2
so
nanometer roughness. RMS roughness is about 2.
RMSE roughness. Okay. So any person who want to ask questions, they can either drop, yeah, they can drop the question in the chat window.
Yeah, sure.
Yeah,
I
we
can
still
stop
have 5 minutes.
sharing and I should be able to see the chat, right?
Yeah,
Yeah.
that is.
Yes. So if anyone else have any other question, you can speak up, unmute your mic, or you can type in the chat box.
Yeah, yeah, anything is okay. Please just ask. Yeah, you know, this is that moment after you've taught a class or given a lecture and nobody asks you anything.
Whether whether everything.
Yeah, you really wonder, and most of the times you wonder, that was probably not a very good talk. So,
It's pretty new field, and also talking about the challenges. I think it's more of understanding the things here. So, I mean, even I would wonder, like most of our new users, I could say, like probably people have not who don't have such facility yet, but interested. So I think it's definitely going to benefit the listeners. So, okay, yeah. So
okay, I
I
can
think
unshare, and I think we are all
yeah.
eagerly waiting for Professor
Okay, we
Javier's
have
talk.
one more question here. We have got 2 questions now before you leave.
Okay.
So,
Other
are there
indenters
any
that could be used. No. We were using a diamond indenter. The material, the standard that we use, to calibrate the area of contact and also to go back and compare our methods with, that is quartz. Quartz is the standard sample that is being indented. The tip is diamond. I'm sorry if I confuse the two during my talk. The tip is made of diamond. The standard sample that is being indented is quartz. And we often go back and check some of our hypotheses by indenting in quartz because we know it very well. I mean, we know its modulus and we know that it's not viscoelastic and so on. Can the same conclusions be assumed for metals? So, see, I used to be under the impression that, for instance, drift is not something that I need to worry about when I'm indenting metals, because but drift is a instrument thing. It has nothing to do with the sample, so drift correction should be done. You should at least check that in your case the drift is linear for the duration of experiments that you're doing, and you are able to correct for it by whichever method. There are lots of methods out there. Okay. Now, which other conclusions? So metals are simpler because there is no recovery during unloading. In SU8, I had a slide, but I think I finally put it away. There are 2 kinds of recovery. There is one recovery that occurs while I unload. The material recovers. And there is a recovery which occurs, if my sample is just sitting in my drawer after I've unloaded. Those are things you don't need to worry too much about metals. But can you measure this area of contact and also to compare our methods with
hello? I think there's some network issue.
I guess Professor Pant's connection has some issue.
Yeah, in the last moment. Okay, no problem. Yeah, Professor Pant, are you still there? Okay. I think she's there. We can see her.
Looks like she got disconnected.
Yeah. Okay. So, yeah, okay. With that, we can conclude the talk, and we definitely thank Professor Prita Pant. I think I'll let you take over to invite Professor Llorca for the next talk.
Okay, so we have Professor Javier Llorca in the next talk. Professor Llorca, so nice to see you after a long time.
Nice to see you, Sandeep, as well.
And thank you so much for accepting the invitation and agreeing to give the talk. So for all to introduce Professor Javier Llorca, he is a professor in Technical University of Madrid, and he is a senior professor, and he is a known name in mechanics of materials throughout the world. So in 2007, he founded IMDEA Materials Institute, which is like a national lab in Madrid. And he was the founding director for 10 years. And then from 2017, he has taken the role of scientific director in the institute. And during that 10 years, he has grown the institute quite a lot and got a lot of funding, exceptionally high quality research and research facilities. And he has multiple awards, and it will be pretty long list to name all, but to name a few. He got Career Award from Spanish Society of Materials, and then he is also fellow of European Mechanics Society and Materials Research Society. He is also associated with some of the works in India, particularly he was Brahma Prakash visiting professor in ISC Bangalore Material Science Department. So I'm very glad to have him as a speaker here. And Professor Llorca, thank you very much again, and over to you.
Thank you very much, Sandeep, for this nice introduction. It was a great pleasure to see you again. Then that's also an honor to be invited to this seminar, and I look forward to the next seminar to be given in Goa presentially in person and not through the network, but hopefully when the pandemic goes
yes,
up,
of course, I also wish so.
We will also be able to travel. So without this, I'm going to try to share my screen to see whether these things work. I guess you can see my screen, can you?
Yes, it's visible.
Yeah, let me check whether, okay, this let me see, okay, whether this is it, yeah. Is it fine? Is in full screen mode now?
On the right side, there is a slide layout. You could close that.
Okay, let me check it out. Let me see what can I do. Okay, let's see. It's okay now?
There is one column on the right side of your screen, which is slide layout. Is it possible to close that?
Let me check it out. Let me see whether, let me check what can be done.
Yes, yes, that column.
That column here, so let's see. Hopefully.
Yes, yes, that is gone now. Now it is good.
Is it all right now?
Yes, would you go for full screen?
Yeah, this is full screen. Do you have full screen or not?
But we see not a full screen view. We see the slide view on the, we see the small slides in the right side as well as the main slide.
Okay, and now do you see the full screen or what do you see?
So we are still seeing the contents on the left,
Yeah. So I don't know whether.
Yeah, this may be better. Yeah,
This
the
is
current
good
view
enough.
may be better.
Yeah, I guess this is not optimum, but and now.
Yes,
oh,
now
yeah,
it's
good.
perfect.
That's good. So then we will use it. This is not full screen mode, but this is going to work. So, okay.
Yeah.
Okay. So I guess without further ado, I guess it's time to begin my presentation because it's time. So as I said before, it's my pleasure to give this webinar on this symposium on recent advancements in nanomechanical testing, organized by the School of Mechanical Sciences in IIT Goa. And the title of my talk, as you can see in the screen, is High-throughput experimental techniques to measure the critical result shear stress for slip and twinning in magnesium and magnesium alloys. So I think it's a complementary talk to the previous talk that was related to viscoelastic materials. This is talking about nanoindentation in metallic materials, in rather complex metallic materials. And in this, let me see what I can do in order, because I have now to pass to the next slide. And this is, okay, let me check it out to see. Okay, perhaps it's better. So this is. So I just want to acknowledge before beginning the talk the work of two of my former PhD students, Jinja Wan and Gustavo Esteban Manzanares, that they did the experimental part and the simulations, and also the work of two former postdocs, Reza Alisadeh and Miguel Monclús, and also the collaboration from two researchers from IMDEA, Dr. John Molina, that is the leader of the nanomechanics program at the Institute, and Professor Yu Wen-Q, that was co-advising the thesis of Jinja Wan, and also the funding from the European Research Council for this investigation. So the outline of my talk is resumed here. So I will begin with the motivation and the objectives. Why are we trying to use these high-throughput experimental techniques, particularly for magnesium alloys? Then I will discuss briefly the experimental techniques that you need to develop for these high-throughput techniques that are diffusion couples and micromechanical testing. And of course, I will focus most of my talk in these micromechanical testing techniques. And then I will show you two different applications of this high-throughput technique to measure the critical result shear stress for basal slip in magnesium aluminum and magnesium thin alloys, and also to measure the critical result shear stress for twinning in the case of magnesium aluminum alloys. And then a third application will be to use these techniques to measure the critical result shear stress for basal slip in the case of magnesium alloys where you have precipitates or where they have been strengthened by precipitate strengthening. And in this particular case, I will just show you some atomistic simulations to reinforce the experimental results. And with this, I will just try to do some conclusions. So, as you probably know, magnesium is the lightest of the structural metals. Because of that, has a lot of potential applications in transport. But not only that, magnesium is also a very good biocompatible material and has an stiffness that is very close to bone. So there is a lot of recent interest in the use of magnesium for healthcare applications, practically in bioresorbable implants. Nevertheless, when you look to magnesium and magnesium alloys, these potential applications are hindered because of the reduced strength and formability at room temperature, and this poor formability and ductility and then poor strength of magnesium alloys can be traced to the particular plastic deformation mechanisms that are induced by the hexagonal cross-packed lattice structure. So if you look to magnesium alloys and you look to the plastic deformation mechanisms, what you can say in the case of magnesium alloys, you have one plastic deformation mechanism that is dominant, that is basal slip. The critical result shear stress for basal slip is very low, but of course basal slip only happens at the basal plane, so cannot accommodate plastic deformation along the z-axis. So in order to accommodate plastic deformation along the z-axis, you either have to have pyramidal slip in the C plus A direction, or you may have to have twinning. And of course, you need this combination of basal slip with either pyramidal C plus A or twinning in order to accommodate deformation in magnesium alloys. What happens is that when you look to the critical result shear stress of magnesium, or the different slip systems in magnesium alloys as a function of temperature, you can see here that there are two systems that are basal slip and twinning that have much lower values of the critical result shear stress. It means that at room temperature or low temperature, the dominant deformation mechanisms are always going to be the same. Basal slip along the basal plane, and if you want to accommodate deformation along the z-axis, you have to have twinning. And twinning is a polar deformation mechanism. So it means that only occurs when shear deformation extends the z-axis of the lattice. So imagine that you have a rolled magnesium alloy like this one that has a very, very strong basal texture. It means that the basal planes are parallel to the rolling direction. Then if you do mechanical test of this material along different orientations, you may have a very, very strong anisotropy. If you load the material in tension along the rolling direction, that is the red curve, on incompression along the normal direction, you cannot activate twinning. Then what you have is pyramidal slip. The critical result shear stress for pyramidal slip is very large, so you have a very, very large flow stress. On the contrary, if you deform this material in tension along the normal direction or at 45 degrees between the normal direction and the rolling direction, you are able to activate twinning. And because the critical result shear stress for twinning is much smaller, you have a very, very low value of the critical result shear stress or the yield strength of the material. So you have a material with a very strong plastic anisotropy. And this very strong plastic anisotropy is very detrimental from the viewpoint of the ductility and deformability. So this is something you just want to avoid. You would like to increase the critical result shear stress for basal slip and for twinning, and decrease the critical result shear stress for pyramidal slip in order to have a material that is more homogeneous or less anisotropic from the practical viewpoint, and then to have higher formability and to enhance the formability and the use of magnesium alloys for different applications. So how do you do that? Well, obviously, alloying has the potential to strengthen basal slip and tensile twinning through solid solution and precipitation hardening. And you know very well that in the case of solid solution, you just modify, put some strains in the lattice, or in the case of precipitations, the precipitates are obstacles to the dislocation motion. So what you have to do is try different elements, alloying elements, to increase the critical result shear stress for basal slip and twinning. But if you really want to measure the impact of alloying elements on the critical result shear stress, then you have different strategies. First of all, you can do the material, manufacture the material, and do tests in polycrystals. But when you carry out tests in polycrystals, it's very difficult to differentiate the contribution for the alloying element that from other contributions that are, for instance, from the grain boundaries or from the texture. So the results are not very precise. Other possibilities is to just cast a single crystal and do experiments on single crystals in a given orientation. But of course, if you want to do that for different alloy compositions, this is very expensive and time consuming. So there is a need for fast and high throughput methods to measure the critical result shear stress of different deformation modes at room and high temperature. And this is basically the main motivation of this talk. So what do we do in this case, or what is the best idea? Well, the best idea to do this is just, to do what are called the high throughput approaches. So the most typical high throughput approach is what is called diffusion couples and diffusion multiples. In a diffusion couple, what you have is you have different materials, different alloys with different composition. And when you do is an annealing treatment, and because you cast a annealing, you have a diffusion. So you have a region in between two parts of the diffusion couple in which you have materials with a constant gradient in composition. And diffusion couples have been used in the past to carry out study thermodynamic phase diagrams. They have been also used to study thermal conductivity and magnetic properties. But basically, diffusion couples in combination with micromechanical testing techniques like nanoindentation or micropillar compression allow a high throughput technique to measure what is the critical result shear stress of different deformation modes for materials with different composition. And these are the two techniques: diffusion couples in combination with micromechanical testing, the technique that we have used in order to try to develop high throughput strategies to measure the critical result shear stress for different deformation modes in magnesium. So what are the objectives of this investigation? The objectives are very clear: to determine the effect of solid solution on precipitation strengthening on the critical result shear stress for basal slip and twinning in magnesium aluminum and magnesium thin alloys using diffusion couples and micropillar compression. So what you do is very simple. You have here a slab of pure magnesium, and you have here a slab of a given magnesium alloy, magnesium aluminum or magnesium thin. And you subject this slab to high temperature annealing, and then you create a diffusion region. And in this diffusion region here, you have, as you move along the diffusion region, different contents of the alloy. And then in a region where the alloy content is constant, you're just using a focus ion beam carved micropillars. So these micropillars here will have a composition that is C1. These micropillars here will have a composition that is C2. And these micropillars here will have a composition that is 3C. And then by testing these micropillars, you are able to measure the critical result shear stress for different deformation modes. Of course, this will depend on the orientation of the micropillars. So you have to do this in grains with different orientation. This is the basic objective. And in order to achieve this, there are a number of challenges that you have to solve. One of these is that you have to understand size effects at the micro and nano scale, because you really want to measure properties that are bulk properties. And when you are going to very small scale testing of the order of microns or below, size effects may be very important. Then we would like to extend this nanomechanical testing technique to ambient and service conditions. So we want to explore high temperature nanomechanics. And then, of course, we want to develop the techniques that are useful to analyze and to study the deformation mechanisms, because we want to be sure that during this test, we are activating the deformation mode or the right deformation mechanism for which we want to measure the critical result shear stress. Okay, so with this, let's go to the development. So the first part in this investigation is the fabrication of the diffusion couples. So what do? You have a slab of magnesium, then you have a slab of a master alloy produced from a master alloy. In this case was magnesium with 9 atomic percent aluminum. You have another slab of magnesium 2.5 atomic percent. You just put them together and do an homogenization annealing treatment that may take at 500 degrees for 15 days. So of course, when you have manufactured this, if you let it enough time, basically there is some diffusion there. Then the second step is you just cut these two parts different and you create the diffusion couple of magnesium 9 aluminum, and magnesium 9 zinc. And then you do a little bit of hot pressing in a Glevel system. You do that to create dislocations and plastic deformation in this region. And these dislocations are going to nucleate many different grains, because you want to have grains with different orientation. And after you have created this diffusion region here with plastic deformation, then you go to step 3, that is the diffusion annealing treatment. So 500 degrees for 300 hours. And then you create this region here where you have a gradient in composition from pure magnesium to magnesium 2.5% atomic zinc, or in this case, from pure magnesium to magnesium 9 atomic percent aluminum. And you have here many grains with different orientations and with different compositions. Apart from that, in the case of the magnesium zinc alloy, we took samples from a region with a given composition, and we carried out the precipitation treatment at 149 degrees for 100 hours to produce precipitates within the microstructure. So just to give you an idea of what you get, this is just one example. This is the slab. This is the part of the slab that is pure aluminum, and this is the part of the slab where you have magnesium 9 atomic percent aluminum. These colors here are the inverse Pore figure. So this corresponds to one grain that has a green orientation. So it's oriented more or less in the -1, 2, -1, 0 orientation. This corresponds to this gray grain that will be here in this orientation. This corresponds to this violet grain that will be in this orientation. And as you move from here to here, what you are doing is you are increasing the aluminum content. So at this point, the aluminum content is practically 0. This is pure magnesium. And as you move here, you are increasing the aluminum content as having 9%. If you carve micropillars along this line, you can see these nice micropillars produced by focus ion beam milling. This micropillar will have a magnesium content that is 100% and 0 aluminum. This micropillar here will have a higher aluminum content, and these micropillars in between will have different aluminum contents. This is for a grain with a given orientation. If you do that in this grain here, then you have grains with different orientation. So in this way, you can have micropillars with different aluminum content and also with different orientation to activate different deformation modes. So this is the next step. So at the end of the day, this is your diffusion couple. You have different grains. And in these different grains, you can different orientations. You can extract micropillars. You are going always to compress perpendicular to the surface. This is the final setup. This is the micropillar. This is the nanoindenter with a diamond flat punch. And in these investigations, we have used two different nanoindenters. One of them is a high-citron PI87 Paco indenter. We have used this nanoindenter within an scan electron microscope, so you can see in situ the deformation of the material. And we have also used a high-citron, a TI950 triple indenter, and this is to carry out the Situ Test. In both of them, we can do tests up to high temperature. Actually, we can go up to close to 700 degrees Celsius, but the results I'm going to present today are limited to 100 degrees Celsius because this is enough for magnesium. In all cases, tests were carried out up to 10% strain under displacement control and to a strain rate of more or less 10 to the -3 second to the -1, so quasi-static conditions. Okay, so let's go to the first case. The first challenge is to try to study or to measure what is the critical result shear stress for basal slip in a material that is a magnesium aluminum alloy or a magnesium zinc alloy with different aluminum or zinc content. So this is the typical micropillar. We use micropillars with a square cross section. We have a lot of expertise of carving these micropillars, so you can see that the taper is very small. Tapering is normally below 1 micron. These are straight micropillars. And we have been able to carve micropillars, all of them with an aspect ratio between 2 to 1 or 3 to 1. This is to avoid buckling during compression. And we carve micropillars with different cross sections, 3 by 3 microns, 5 by 5 or 7 by 7 to study size effects because we wanted to study. All these micropillars were carved in grains that were suitably oriented for basal slip. So this is the orientation of the crystal within the micropillars. Of course, these are single crystals. And as you can see here, that the Smith factor for basal slip in all these cases is very high, very close to 0.5, while the other potential deformation mechanism that you can activate, that is twinning, has a very much smaller Smith factor. So because the critical result shear stress for basal slip is the smallest one, and because of the difference in Smith factor, we are almost sure that when we do the formation, we are only going to activate basal slip. And as you can see here, we are going to measure the critical result shear stress in pure magnesium, magnesium 4 atomic percent aluminum, magnesium 9% atomic aluminum, and then magnesium 1.5 and 2 atomic percent zinc. So that means that we have a lot of different compositions. The load displacement curves from the Nanoindentation were transformed into stress strain curves from the micropillar dimensions using the Sneddon correction to take into account the deformation of the bulk of the material. And of course, when you have the engineering stress strain curve, you can transform into the result shear stress strain curve. That's what you want to measure the critical result shear stress using the Smith factor that you know for the given crystal orientation that you have here. Okay, so let's go just to one example. This is the results of mechanical test. This is pure magnesium. This has been tested at 25 degrees Celsius. And these are the results shear stress versus engineering strain curves. And these are for micropillars that have 7 by 7 microns cross sections, 5 by 5 microns cross section, and 3 by 3 microns cross section. One of the things that you can see is that you have a gradual yield of the material in all cases. This is controlled by the gliding of pre-existing mobile dislocations. But because the micropillars are small, particularly in the 7 by 7, there is a point in which basically you have a lot of hardening because you do not have enough dislocations to accommodate all the plastic deformation. You are increasing the stresses, and then you have here a pile up. Sorry, you have a localization of the formation. So you activate one of these sources, and then you have the formation of an slip band. And of course, as you increase the size of the pillars, you have more homogeneous deformation, and then the amount of size effect that you have is decreasing. So what you can see here is that you have to be very careful, because if you have very small micropillars, you cannot say that this is the critical result shear stress for basal slip, because what you have here is size effect, and this value of for the onset of the formation of an slip band is controlled by the small dimensions of the micropillar, and is also controlled because of the limited number of dislocations on the initial micropillar. If you go the same thing to high temperature, you can see that the situation is somehow similar, somehow different. When you go to 100 degrees Celsius, again, you have localization of the deformation, you have the formation of some slip bands there, but as you can see that the size effect is much smaller. And actually, if you consider this point here, that is the point where you really start to have non-linear deformation, this will be the point that corresponds to the critical result shear stress for basal slip. You can see that at higher temperature, size effects are reduced and the pop-ins are reduced. And basically, in this particular material, size effects are negligible when the size of the pillar is over 5 microns and the temperature is 100 degrees Celsius. So with this technique, we can really measure the critical result shear stress using micropillar compression. This is just for pure magnesium. But what happens if we go to a magnesium aluminum alloy? So this is the case for a magnesium alloy that has 9 atomic percent of aluminum. This has been tested at 25 degrees Celsius. And these are the result shear stress versus engineering strain curves. And as you can see here, for the very small micropillars, you have a linear behavior, and then you have the localization of the formation of strain groups. So you can see that the pre-existing dislocations in this material, in the 3 by 3 microns micropillar, are pinned by the solid atoms, and then plasticity develops abruptly with the activation of a few dislocation sources. So deformation tends to localize in a few slip planes. As a result, when you alloy the material with aluminum, the magnesium with aluminum, size effects are much more important, and this is something that you have to take into account. If you want really to see this localization effect and see how the formation progress, then you can go to the in situ test. So what you are going to see here is a movie of an in situ test of a micropillar of magnesium 9 atomic percent aluminum with a size of 3 by 3 microns, where you are going to see the localization of the deformation. So this is the load. Initially, you have what is a linear behavior. This is a purely elastic deformation. There is no plastic deformation because you are not able to activate dislocation sources. And as you will see, all of a sudden, there is the formation of an slip band. And this is when you have these tremors. So you can see here very, very well how the localization of the deformation happens. That's what happens when the micropillar is 3 by 3 microns. If we go to other micropillar, it's the same material, but in this particular case, the micropillar has a dimensions of 5 by 5 microns. You can see that there is a large difference in the deformation mechanisms. Still, you begin deformation, you have linear deformation, you see a red line. But here at this point, you start to see that you have some pop-ins of plastic deformation. You have here one pop-in. It's difficult to see. You will see the slip bands here later on. And then you increase, and then you have another pop-in, increase again, and another pop-in, and more and more. And basically, you are activating different dislocation sources. And as you now you can see here this slip band that has from here, and there are more slip bands. So you can see that the formation is more homogeneous. So as you increase the micropillar dimensions, the formation is more homogeneous, and you have less localization. And this has to do with the initial number of dislocations that you have in the microstructure of the material. So then we were able to do this in this same material at high temperature. This is the magnesium 9% atomic aluminum tested at 100 degrees Celsius. And you see here the same behavior that we saw in the case of pure magnesium. When you go to 100 degrees Celsius, the difference between the curves with the micropillars of 5 microns and the micropillars of 7 microns are much more smaller. The formation is much more homogeneous. So you can see that in this particular case, when you go to high temperature, you can really measure the critical result shear stress for basal slip in these materials. So taking all these things into account, I would show you these are the final results of solid solution strengthening. The results you have here correspond to all the micropillars that have a section of 7 microns by 7 microns, so where size effects were minimum. The red line here corresponds to the pure magnesium, and then you have lines in different colors. Blue and orange are, blue and black corresponds to the magnesium aluminum with different aluminum contents, and orange and green corresponds to the magnesium zinc with different zinc contents. And you can see very clearly here the strengthening effect of solid solution on the critical result shear stress for basal slip. In the case of the tests that were carried out at high temperature, of course, the size effects were less noticeable, and it was easier to determine accurately the strengthening provided by solute atoms of aluminum zinc on basal slip. So this is really a high throughput methodology, because if you want to obtain what is the critical result shear stress for basal slip in these four different magnesium, aluminum, magnesium, zinc alloys using standard techniques, you will have to cast a single crystal, you have to carry out the mechanical test, and then it will be very, very time consuming and very expensive. So let's see how it looks like. These are just a summary of the results we obtained for the solid solution strengthening effects in magnesium aluminum. This is the increase in the critical result shear stress as a function of the aluminum content. The black and solid and open symbols are results from the literature. There are very few data from the literature. This corresponds here to the results from ACAR here, and this corresponds from Cáceres in another study, this case in polycrystals. These are tests in all cases to 100 degrees Celsius, and the red lines are our experimental data. And as you can see, the experimental data that we obtain with our micropillar compression test fit extremely well with the results obtained in the past for single crystals and polycrystals. And they tell that the strengthening due to the solid solution in magnesium alloys follows the Labouche model, that is a very well-established model. So that validates this high throughput technique to measure the critical result shear stress, or the increase in critical result shear stress in magnesium aluminum alloys due to solid solution strengthening. These are the results for solid solution strengthening effects in magnesium zinc alloys. In this particular case, the amount of data in the literature is extremely limited. These are the only data in the literature in the past, and again correspond to some work by ACAR 30 or 40 years ago. This is some work on a super-saturated single crystal that is more recent. And again, these red points are our experimental data. And of course, our experimental data using micropillar compression are in agreement with other data using standard single crystals. We can see here also that the Labouche model also is applicable for the case of magnesium zinc alloys, but the slope of the Labouche, the coefficient of the Labouche model when you have high zinc content is different than when you have low zinc content. And basically this can be explained because of the tendency of zinc atoms to solute clustering and short range order that may increase the strengthening effect. In any case, one thing that you can see that is important, that when you can see the solid solution effect, strengthening effect in magnesium alloys, both for basal slip, for both zinc, or in the previous case, for aluminum is very small, you only increase the critical result shear stress by 4, 5, 6 megapascals in the case of aluminum, and by a similar amount in the case of zinc. So it means that still basal slip continues to be the softest slip system, and the main objective that was to increase the critical result shear stress for basal slip to decrease the plastic anisotropy was not achieved in this particular case. Okay, this is what's going on in the case of basal slip. Let's go to a more complicated case, that is the case of twinning. Because twinning, as you know, is a rotation of the lattice, that in the case of magnesium, normally you have tensile twinning. And when you have tensile twinning, this parent grain that is oriented in this direction rotates almost by 90 degrees and takes a completely different orientation. So this is the 86 degrees orientation that is typical of twinning. So basically what we did, we have a micropillar, again, very low tapering, different cross sections, 3 by 3, 5 by 5, 7 by 7. And this micropillar is oriented in this orientation here. So when you compress the micropillar, you increase the length of the Z-axis, and this micropillar is very well oriented to produce twinning. So when you look what is the critical result shear stress for tensile twinning, you can see that it's much higher than the critical result shear stress for either prismatic slip or pyramidal slip. And one thing that is important that you have to realize that when you nucleate a twin rotates the lattice. So after twinning, you have a crystal with a different orientation. And in this particular crystal with a different orientation, you may have pyramidal slip because the critical result shear stress for pyramidal slip has increased in the twin crystal. And also you have a non-negligible Smith factor for basal slip. In the untwined material or the parent material, the Smith factor for basal slip was practically 0, so you cannot have basal slip. But in the twin material, you may have basal slip. So this is a much more complicated phenomenon, and the analysis of these results is much more complicated. So let's go here, and then I guess I need to activate the play, just at least for some time here, for the sake of clarity. So this is the typical result that you get here of the engineering stress and engineering strain curve of one crystal that is oriented by twinning. You have an initial linear region, then you have a pop-in, the load goes to 0, that means some phenomenon has occurred that you will see twin nucleation, and then as you deform more, the micropillar punch gets in contact with the micropillar, and then you have a region when you have practically constant deformation or deformation at constant stress, and then you have a strong hardening. And what we did is to do interrupted test. So basically we carry out a test up to this point and then stop the test and look to the deformation mechanisms in the SEM, and also do TEM and do transmission Kikuchi diffraction from thin lamillas extracted from the micropillar to see what was the orientation of the lattice at this point, point B, at this point that was point C, and at this point here that was point D. And this is what you are going to see. So in point D, this is what B, this is what you see. And when you take a lamella and do transmission Kikuchi diffraction, you can see that this is the parent grain, but two twins have been nucleated in the upper part of the crystal. So this low drop was due to twin nucleation. Then you deform the crystal along this line and you go to point C. And when you go to point C, this is the shape of the pillar, about deformation about 6%. And what you can see here is that the twins have grown. So you practically, the two twins that do twin variants, they have grown and they occupy most of the pillar. So now your pillar has a completely different orientation. That was the original orientation of the pillar. We were loading in the vertical direction. Now you have two twins and the pillar has rotated the crystallographic lattice. So in this region here, now we are going to activate different deformation mechanisms. That's the reason why we have this hardening. And basically, when you go to 10%, you can see that you have a little bit of basal slip. And this is because now the Smith factor for basal slip is not 0. But basically, when you go to higher, you can see here that you have a lot of plastic deformation due to pyramidal slip. So at the end of the day, this is what, so let me go back. So at the end of the day, with this test, you can measure from here the critical result shear stress for twin nucleation. And this here is the critical result shear stress for twin growth. And finally, as I told you, when you have deformed the pillar up to 10%, this is a TEM image. And basically, in this particular orientation, where you have the zone that is 2, -1, -1, 0, and the G vector is 0, 0, 2, in this region here, you have the visibility condition. So you can see this location with C components. This is for the twin material. This is in the parent. In the parent, you don't have C component dislocations. But when you go to a different G vector, you can see that you have A dislocations here. So basically what you can see that in the twin, you have C plus A pyramidal slip, while in the parent, what you get is basically basal slip that is there. So that means that you get a lot of information. And then these are the typical results. This is micropillar compression in magnesium aluminum alloys with different aluminum content, 0%, 4%, and 9%. In micropillars with different sizes, 3x3, 5x5, 7x7, oriented for twinning. And you get always the same response. You have the onset of twinning, then a flat region, and then hardening. From this point here, you can get what is the critical result shear stress for twin nucleation. for this more or less flat region here, you can get what is the critical result shear stress for twin growth. And then this hardening here is due to pyramidal slip. And actually, if you do some analysis, you can also get what is the critical result shear stress for pyramidal slip as a function of the aluminum content. So these are very, very rich tests. You can see that there is a size effect. The red are the pillars 3 by 3, the black, the pillars 7 by 7, and the blue, the pillars 5 by 5. But as you can see here, the size effects in the case of twinning or pyramidal slip are much smaller than in the case of basal slip. So at the end of the day, these are the results of our investigation. This is the critical result shear stress for twin nucleation as a function of the pillar size. These are the values in red for pure magnesium, magnesium 4% aluminum, and magnesium 9% aluminum. And those are similar values for the case of twin growth. As you can see, if you put up to 4 atomic percent of aluminum, it doesn't change very much the critical result shear stress for twin nucleation and growth. But when you go to 9% aluminum, there is a clear increase by that. The effect of micropillar size on the mechanical behavior is negligible for micropillars with dimensions above 5 microns. So at the end of the day, this is the effect of aluminum content on twin nucleation and twin growth and the critical result shear stress. This is the critical result shear stress for twin nucleation and for twin growth. And these are unique results. Basically, this is a comparison of the increase in the critical result shear stress for twin nucleation and growth as a function of aluminum content. There is only one model for this, and our results, at least for low aluminum content, are in agreement with the model. But basically, this is an explored area, and these are new results that will have to be validated by simulations, things like that. So we conclude that the critical result shear stress for twin nucleation is higher than for twin growth, that aluminum in solid solution increases the critical result shear stress for both twin nucleation and growth, and the Labouche model is okay for dilute conditions, but it's not okay when you have higher concentrations. So at the end of the day, this is just a summary. With this technique, we have been able to measure what is the critical result shear stress for basal slip, for twin nucleation, for twin growth, and also for pyramidal slip. In magnesium 4% aluminum.
Professor Llorca, I believe the slide did not change.
Okay. Okay, you see it here?
Yes, now we see the summary slide. I guess one or two slides didn't change. Yeah, we are in the summary slide now. We see that.
So basically, we were able to measure the critical result shear stress for basal slip, twin nucleation, twin growth, and pyramidal slip. In magnesium 4 atomic percent aluminum and magnesium 9% atomic aluminum, with just a very, very small effort as compared to all the effort you would need if you have to cast the different aluminum magnesium alloys and you have to cast crystal with different orientations. And then we can look what is the effect of the anisotropy. This is the ratio between non-basal to basal slip for the critical result shear stress. And as you can see, when you add a little bit of aluminum, you reduce the anisotropy for all the deformation modes, but still there is a strong anisotropy between non-basal and basal slip modes. So with adding aluminum, you cannot reduce significantly the plastic anisotropy of magnesium alloys. This is something that more or less was known, but basically what we have developed here is a new technique that allows us really to do high throughput analysis of that. Okay, this is for materials that have been strengthened by solid solution, but let's try to see what we can get in the case of materials that have been strengthened by precipitation. So again, I'm going to change to the presentation mode. So what we did is take a magnesium 1.5 atomic percent zinc and H. And then what we did is to produce a very nice distribution of beta prime 1 precipitates. These beta prime 1 precipitates, as you can see, they are long rods that are parallel to the z-axis of magnesium. And this is the cross-section of these long rods. You can see they have a diameter of about 10 nanometers, things like that. When you go to high resolution, this is the basal plane, and these rods are perpendicular to the basal plane. So we were able to measure the length of these precipitates is about 100 nanometers, and the diameter, as I said before, is of the order of 10 nanometers. So what we did is take micropillars of these materials that are well oriented for basal slip and do compression test of these micropillars. And these are the result shear stresses, a function of the strain, for pillars with different dimensions, 1 by 1, 3 by 3, 5 by 5, 7 by 7. What you can see here immediately is, even though we have localization of the deformation in all cases, the size effect when you have precipitate is much smaller. Actually, between 3, 5, and 7 micrometers, the curves are almost superposed. So the presence of the precipitates reduces significantly the size effects. So that's good news for micromechanical testing. We also did tests at different temperatures. So these are for 2 different aging treatments. This is the peak age condition. This is the overage condition. The blue are the critical result shear stress, so the result shear stress versus strain curves at room temperature, and the red ones are at 100 degrees Celsius. And one thing that is interesting here is that when you increase the temperature a little bit, from 23 to 100 degrees Celsius, there is a huge reduction in the critical result shear stress. And this is surprising because normally precipitate strengthening is known to be an thermal mechanism. But of course, something is going on here that makes that this is a thermally activated mechanism in this particular case. We just looked to the deformation mechanism. So we just took one micropillar, make a thin lamella parallel to the micropillar, and then look it in the TEM. And when you do that, you can hear, this region, you have basically slip bands where the formation has been localized. And when you go to higher magnification, you see these very nice pictures. These are the traces of the basal plane, and these are the precipitates. And you can see very clearly, like in this case, basal dislocation have been able to shear the precipitates. Actually, this is what happens at room temperature. But if you go to high temperature, the effect is exactly the same. And sometimes in some regions, the basal dislocation have completely destroyed the precipitates. So this was somehow surprising because normally these precipitates are incoherent. And incoherent precipitates are normally not sheared by dislocations in other metals, but in case of magnesium, these incoherent precipitates can be sheared by dislocations. So we just really wanted to know what were the mechanisms that were responsible for that. And in order to do that, we did some simulations. So basically what we did is we do a molecular dynamic simulation. This is the precipitate, this is the basal plane, and we use a molecular dynamic simulation where the precipitates are long rods that are perpendicular to the basal plane. We took a lot of care to build up the interface between the precipitate and the matrix, taking into account that these are minimum energy interfaces. This is something that is important. And then this is the model for the atomistic simulations. So you have a domain of 35 by 40 by 40 cubic nanometers. In this domain, this is the basal plane. In this basal plane, you have a basal dislocation that is dissociated, and perpendicular to the basal plane, you have the precipitate. Basically, we have 2 different types of precipitates. We have a small precipitate that is 2 by 4 nanometers in cross section, and we have a much larger precipitate that is similar to the experimental one. And what we do is we apply shear strain parallel to this layer and parallel to this layer, and then the dislocation moves and interacts with the precipitate. And this is basically what you get here. This is the shear stress versus the shear strain, and these are the stress strain curve you get. You can see, you will see in the movie. So this is the first dislocation that passes and makes a loop, the second, the third, and finally you can see how the dislocation is able to shear the precipitate. And shearing is not localized along one crystallographic plane, but what creates is a disordered region in the precipitate. So this is interesting because this was very close to the experimental information. So what you see here is basically the shear stress versus the shear strain. These are at different temperatures. The curve in black is for 0 Kelvin, 100 Kelvin, 300, 400 Kelvin. And as you can see, this point here indicates when the dislocation pile up is able to shear the precipitate. So this movie tells you what is happening at 0 Kelvin. First dislocation passes. Then the second dislocation passes, we are here. Then the third dislocation passes, we are about. And then when the fourth dislocation passes, the fifth, the sixth, the seventh, when we reach this point, you have been able to shear the precipitate, and the precipitate is completely disordered. So you get this value of the shear stress. This is what happened at 300 Kelvin, the blue. So the first dislocation passes, the second dislocation passes, the third dislocation passes, and then when you have the fourth dislocation passes, the precipitate is completely shear. So what you can see here is that dislocations are able to shear the precipitate, and the number of dislocations that you have to pile up in order to shear the precipitate decreases as the temperature increases. There is a strong effect of temperature on the critical result shear stress. Actually, what is interesting is that, again, we are going to go to the presentation mode. This is just the precipitates after being sheared by dislocations. You can see here very clearly how the precipitates have been sheared. This is a high resolution TEM picture. So you can see here how one precipitate is about to be sheared, and another precipitate has been sheared. And these are the results of the molecular dynamic simulations. And you can see here the formation of the kink. So it's very clear that these molecular dynamic simulations show very clearly that what is the shearing mechanism that is similar to the experimental one. So this confirms why we have shearing of the precipitates and the reduction in the critical result shear stress. So just to end up, I have presented a high throughput experimental methodology to determine the critical result shear stress of different slip systems and twinning in magnesium alloys. The methodology is based in the combination of diffusion couples with micropillar compression tests and can be applied to solid solution and precipitation strengthened alloys. Novel values of the critical result shear stress for slip and twinning were obtained as a function of aluminum and zinc contained in solid solution, and also for precipitation hardened magnesium thin alloys. What is more important besides the quantitative results is that this methodology can be easily expanded to obtain the critical result shear stress of any alloy, and it's a high throughput methodology that provides very accurate results of the critical result shear stress at a much lower cost than the typical technique that involves casting single crystals and doing mechanical tests in single crystals. And that's all, and I just thank you for your attention.
Yeah, many thanks, Professor Llorca, for a beautiful in situ nanomechanical testing talk and presenting this work. We have a couple of questions here. Okay. One from Professor Prita. She's asking, is there an advantage in fabricating pillars with square cross-section instead of circular cross-section? Yeah,
that's a good question. Yeah, there are two advantages. First of all, that when you manufacture pillars, I'm gonna share my screen again because it will be easier. When you manufacture pillars with a square cross-section, it's much easier to reduce the taper, because you can rotate the micropillar and reduce the taper on each one of the surfaces. So there's one reason. Tapering is reduced. The second good thing is that if you want to see what is the slip trace of the active deformation mode with the pillar surface, like for instance here, this is much clearer because this is a flat surface. So from the viewpoint of identification of what slip system is operative, here you have basal plane here, but when you come here, this is also basal slip. It's much easier if you have flat surfaces that you have them in the square pillars. So these are the two reasons why we use square pillars instead of circular pillars.
So yeah, Professor Prita, if you have any follow-up questions, you can unmute.
Thank you very much. I have a separate question on the simulations that were showed at the end, but I'll hold on. There's another question in the chat.
Yeah, so the another question is from Himanshu. He's asking, can basal slip alterations in magnesium be used to activate prism slip?
Well, that's actually a good question. So normally cross slip in magnesium is difficult because the energy for cross slip from basal slip to prismatic slip is too high. Actually, we have some recent evidence of my former student that she's now working on China, that you can do that in the case of magnesium calcium zinc alloys. Particularly the addition of calcium reduces the energy barrier for cross slip, and then in this case we have seen evidence of basal to prismatic cross slip during micropillar compression? So the answer is yes, but you have to choose the right magnesium alloy, because in pure magnesium, the energy barrier for cross slip from basal to prismatic is too high. And also the critical result shear stress for prismatic slip is also too high. So it's not normally seen.
Okay, thanks. So Professor Prita, you wanted another question?
Yes, I just had one more question about the simulations that you showed in the end, where these precipitates are seen to be sheared.
Yeah.
So if I understood, you said that these are incoherent precipitates, right?
Yeah.
And we keep teaching our students that, look, incoherent precipitates, because there's no continuity of slip systems, dislocation cannot go in. So is it like a hall patch like thing that you're seeing, that there is a pile up, and then eventually the stress on the leading dislocation is enough to push it through?
Yeah. So that's some new discovery. I mean, these results are recent, were published, just last year, and there is more evidence coming up. So the standard knowledge is that you have coherent precipitates, then dislocations in the matrix can go into the precipitate because they share the slip plane, and that's fine, that's true. But then you go to I'm gonna share the screen again. Then we start to do this mechanical test. And when you do this mechanical test here, obviously you can see that the dislocations are shearing the precipitates. But when you go to higher magnification, you really see that this shearing of the precipitate is not through a crystallographic plane. And then this is when we decided to do the MD simulations. And when you do the MD simulation here, we saw that there was a auto-one loop, another auto-one loop, but finally the dislocation was able to go through, and this is what we saw. And as you can see here, fracture does not take place through a crystallographic plane. You are piling up dislocation, the stresses are higher and higher and higher, and there is a point in which basically you create a region in the precipitate that is completely disordered. So this is something that I guess eventually will happen in any precipitate. If you pile up enough dislocations in front of the precipitate, the stresses at the leading dislocation will be so high that we'll be able just to destroy the lattice of the precipitate.
Okay, yeah, this is really fascinating. Thank you.
And that happens particularly in magnesium because, dislocations in magnesium pile up in the basal plane because the critical result shear stress for slip dislocation in the basal is so low that it's very easy to create pile up of dislocations. That's the reason why eventually you have so many basal dislocations that they just destroy the precipitates. It's not that they cut them, they just, you can see, you go to this TEM image here. This is high temperature, but this is the same. You can see in this region here, the precipitates have almost disappeared. So the stresses were so high that they have been, or here you can see the precipitate has been kinked. So this is not crystallographic slip within the precipitate. This is just pure stresses, brute force, so to speak.
So are we less likely to see this in more symmetric materials or materials which have less of a inhomogeneity in Schmidt factor, because there'll be other pathways?
Yeah, so the question that makes magnesium particular for that is that the critical result shear stress for basal slip is much lower than for any other slip system. Mm-hmm. If you have FCC materials where, of course, you have the same slip system but different planes, you are going to activate several of them. In the case of magnesium, very often you only activate one slip system, that is basal slip. And this is regardless of the grain orientation, because the critical result shear stress for basal slip is very often 1 order of magnitude smaller than the critical result shear stress, even for twinning or for pyramidal slip. So this process is, I would say, particularly important in the case of magnesium alloys. And that's the reason why magnesium alloys are very difficult to strengthen. Because even if you put precipitates, these precipitates, sooner than later, they're going to be shared by dislocations. So that makes difficult strengthening of magnesium alloys.
Okay, thank you very much.
You're welcome.
Okay, great. Thanks, Professor Yorka. So, because of the time limit, we conclude this talk for now, and then we go to our last talk. So, Sandeep, I pass it to you.
Yes, so thank you very much, Professor Yerka again.
Thanks again.
So next speaker, next seminar we have from Dr. Asif. So Dr. Asif currently is managing director of the Industron Nanotechnology. Before that, he was managing director of R&D division of Bruker Nanosurfaces. He is an Oxford PhD, and his alma mater is also ISC Bangalore Material Science. And he has 22 patents and 4 R&D 100 awards, and also he has many journal publications. So we are glad to have him on board. It's pretty late night, or I should say early morning. We are grateful that he is still up and to speak to us. Thank you very much, Dr. Asif, and over to you.
Thank you. Thank you for the nice introduction. Yeah, greetings from Minneapolis. I did sleep, but then I got up around 3 a.m. To participate here. So it's nice to be with you all. And I think with that, I think I have my control on the.
Yep, you should be able to share the screen.
Okay. And
the green.
Okay. Can you see my slides now?
Yeah, it's in the grid form. So
okay, that's good. So if it is in grid form, I can go from there. Okay. So thank you again for the invitation, and also thank you for Pratyank and IIT Goa for organizing this webinar, mini symposium. So I heard the talk from Professor Prita, and thanks to her that I don't have to talk about the basics of nanoindentation. So I'm going to go continue the same way that she finished with depth sensing inundation. And then I will go a little bit on the next level of instrumentation that is available that can help to resolve some of the issues that she mentioned about drift and other things. So that's my part of my talk. So I think by now most of you probably are already familiar with what is a nano inundation technique. And here what I'm trying to do is basically what you can combine with this nano inundation technique, which we call is a kind of a hybrid technique, and then make use of the full suite of the instrument. Okay. So nano inundation is basically a depth sensing technique where you apply a load and measure the penetration of the indented tip into the sample as a function of load. Okay, and then like Prita presented, that you measure the stiffness from the unloading curve and calculate the hardness and modulus of the material through this Oliver and Farr method. Okay, that is straightforward nano inundation technique. Okay. But if you combine that technique along with, for example, if you can heat the sample, cool the sample, or you can do it at any environment, I call it as kind of a hybrid technique. Or you can also combine with we have this in situ scanning probe microscopic capability where you can go on and get the topography of the surface. Or you can do at a kind of a dynamic load. There are techniques called modulus mapping, high throughput mapping. These are all the 3 things that I'll be covering in my talk today. And then Professor in the previous talk, he presented about the doing experiments in scanning electron microscope. You can do the same thing in transmission electron microscope. Or if you have a Raman microscope, you can do this mechanical test and measure the Raman spectra. You can do it on a biological microscope, or if you have an X-ray instrument, you can do that in situ and see what the crystallographic directions and orientations and how it is getting deformed. And it can also combine with the chemistry, electrochemistry, and the electrical characterization. So there are multitude of techniques that you can do along with nanoindentation. And so over the period of like 25 years, we developed these things. So, and today's talk, I'm going to particularly talk about dynamic mechanical analysis and how that can be useful in alleviating some of this problem that Professor Prita Pant mentioned in her talk. And I'm also going to go present high throughput mapping technique. Basically, it's essentially a depth sensing inundation technique, but you're doing it at much higher much higher speed to get the property of the map of the surface. So I'm going to cover that in the later part of my talk. Okay. So in Nanoindentation, as you are all familiar, what you get is the load displacement curve, and that we call is the quasi-static test where you apply a load and measure the displacement as a function of the load. Okay. The important part is basically you have to measure the stiffness of the contact, that you do it through by analyzing the unloading curve. That is where Professor Prita Pant mentioned that if you do it over a period of time, you'll have problems with the drift. And also, I think another important aspect is with respect to viscoelastic material, these unloading curves behave differently, and depending upon the portion of the unloading curve that you take and analyze the stiffness, you may get a different stiffness as depending upon how much percentage of the curve that you take. Okay. And so there will be a lot of problem when you have kind of a viscoelastic material. So some of these things that she already presented. To avoid that, we introduce a simple technique, which is a force modulation technique, or in other ways we can call it as a dynamic mechanical analysis at nanoscale, where what we do is we superimpose a small sinusoidal force on top of this quasi-static force and measure the displacement response for the application of the force that you do. This is very quite similar to how you do this with, for example, you do it at a particular frequency and measure the response at that particular frequency. This is similar to how the way you do the radio broadcast, where you do it at a frequency from the transmission point of view from the station, and then at the receiving end, you tune it to that frequency and you listen to the radio, right? It's the same way. So you oscillate this force at a known frequency, and then you have the electronics to only listen to at that particular frequency how the transducer responds, how the material responds. So for that, we use a lock-in amplifier. Is basically nothing but a vector amplifier where you can be able to listen to that particular frequency and measure the response. Okay. So in a very simple way, you apply oscillatory force, that is F sin omega t, and then you measure the displacement response, and then from the relationship between the applied oscillation and the measured displacement response, you can infer many things. For example, when you do it on a elastic material, the force and the displacements will be in phase. There won't be any phase shift between this force and the displacement. And that is typically for an elastic material. But if you do it on a viscoelastic material, because of the nature, there is a damping. What it will do is it will kind of delay the response so that you have a phase shift between the force that you applied and the displacement that you measure. So typically in an experiment, we apply an oscillatory force of known amplitude and measure the displacement amplitude, and also measure the phase shift between this force amplitude and the displacement amplitude. Okay, that will then if you take that measurements, for example, in this case, by using first year physics of a linear oscillator, if you know what the force amplitude that you apply, you can calculate the displacement amplitude using these analytical equations, provided that you know what the constants is. For example, that any transducer which has a mass, because you have a tip, you have springs and things like that, and it has a stiffness due to the spring. So these are all the things that I have shown over here. And then there is a damping, the damping within the transducer, also damping when you make contact with the sample. So these parameters, for example, at least if you know for transducer, then you can calculate for the material. Okay. So this is a very simple mathematical model, that is simple harmonic motion that you can use. Then if you know what the force you apply, you can calculate the displacement, and you can also measure this displacement from the lock-in amplifier. And also you can measure the phase shift between the force and the displacement. That is what I'm showing over here. So the whole important thing is basically the main focus is how do we can measure the contact stiffness when you do this experiment, because the most important measurement that you have to do in nanoindentation is the stiffness of the measurement. Okay, as long as you make the stiffness of the measurement correctly, and then if you have a good area calibrations, you will end up having nice measurement. So that is where when you measure this stiffness by by this force modulation technique, and that gives you a better sense of measuring the modulus and hardness of the material. The reason is, like Professor Prita Pant mentioned, that when you do in a quasi-static manner, depending upon the drift in the instrument, you probably be measuring the drift of the instrument along with your actual measurement, and it is very difficult to kind of deconvolute the actual measurement from the drift. But when you do at a much higher frequency, because the drift is a kind of a low frequency phenomena, now if you do the experiment at much higher frequency, you can avoid this drift problem and you can straight away go and calculate the stiffness. Okay, so that is the basic difference between the quasi-static and dynamic technique. In both the technique, what you measure is the stiffness. In a dynamic technique, along with the normal stiffness that you measure, you also measure the loss component of the stiffness, depending upon the damping of the material. And then if you take the ratio of this, the storage stiffness and the loss stiffness, you will get tan delta, which is characteristic of the damping of the material. Okay, so it is very useful for viscoelastic material. So what I mean by loss and storage is, for example, if you throw a ball, let's say you drop a ball from a height, it bounces back to a certain height. In that, if you take the same analogy, there is a total energy and there is a recoverable energy. That the recoverable energy is what we call stored energy, and the loss is what we call loss energy. So there is a storage component, loss component. Depending upon the viscoelastic characteristic of the material, it may differ from one material to another material, from one frequency to another frequency. Okay. Now, along with this inundation technique, where you can measure in quasi-static technique, is basically what we call is the storage modulus of the material, or the reduced modulus of the material by measuring the stiffness. In dynamic inundation, you get, like I mentioned, you can measure both the storage and the loss component. Okay, so if you do it on an elastic material, what you measure is the stiffness as a function of depth, and then if you convert that stiffness and the depth information into hardness and modulus, you can measure this property continuously as a function of depth. So in one single indentation test, you can do like hundreds of points along the indentation path, and you can measure this property as a function of depth continuously. That is a big difference in doing this in dynamic way compared to in quasi-static way, where you have to do load and unload, and you have to do at the different depths at different locations. And so it takes much more time, and you don't have a much higher of a data density, whereas you can do all that information as a function of depth at a single location within a minute or so, and you can get the high density of data. So even for elastic materials, for like some metals and ceramics, if you wanted to do a depth profiling, this technique is very useful. Okay, it's very useful for a polymer material. Like I mentioned, that when the polymer material have a viscoelastic response, you have this the dynamic technique that allows you to measure the properties of the material as a function of frequency. Okay, and if you have to do equivalent in quasi-static techniques, you have to load and unload at different rates, and then you have some kind of limitations. Whereas if you do it in the way that I described, you superimpose a small oscillation and measure the displacement response. And these oscillations are very, very small. We call it a small signal approximation. The oscillation amplitudes are very small, that the contact size is not changing when you do the oscillation. And then you can also change the frequency of this oscillation. So in a nutshell, that you can directly go and measure this viscoelastic response of the material by measuring the storage and loss modulus of the material. For example, I have given for a polyethylene polymer here, you can see that the loss modulus as a function of frequency is decreasing from 0.1 Hz to 100 Hz, and for the storage modulus is basically increasing as a function of frequency. This is what typically you will expect for a polymer material to behave. And if you take this ratio of this loss to storage modulus, you get basically the tan delta. So this is what we can do with the DMA technique. Okay. Now, if you have this capability of changing the temperature, then you can do that at a different temperature. Like here, I'm showing it for a PMA material, where these experiments were done at different frequencies but at different temperature. Then by looking at this data, we can collectively construct a master curve, which is very, very useful for the polymer chemist. Okay. then you can kind of understand how the properties are changing. For example, in this case, the storage modulus as a function of frequency and as well as function of temperature. Then you can at some temperature, you can see this glass transition, and you can also observe that from the tan delta curve that you can see at the bottom. So you can pretty much completely characterize the viscoelastic characteristic of the material by doing these experiments. Okay, so this is another example where this is for a polymer thin film, which is very difficult to do with any conventional DMA technique, where we can do it on the nano scale. By doing this method, we can measure the storage modulus as a function of temperature, from cryogenic temperature to a higher temperature, and as well as we can calculate this tan delta as a function of temperature. From that, we can calculate the peak position and the glass transition temperature and all of that. Okay. So this is whatever that I have talked so far is basically measuring the property at one location, where you, the same way that you do the depth sensing inundation, you apply a load, measure the displacement at one location. But if we can also extend this to kind of a mapping technique, where we can scan on the surface, but continuously measuring the response as you scan. For example, you just measure the contact stiffness or the last part of it and storage part of it, and then scan on the surface the way you do this SPM imaging, like you do it in AFM or in our system, in situ SPM imaging. You can measure this mechanical response as a map, okay? Which means that on viscoelastic materials, not only you can measure the properties, but you can also kind of construct the map or the image format, okay? So this is kind of I'm showing it you in a cartoon video, where you can see that you scan on the surface at the same time you oscillate and then measure the response. Basically, you measure the stiffness response as you do that, and then by line, you can kind of construct the response. And as you can see here, for example, in situ SPM imaging, you measure the topography. Along with the DMA, you can also see the phase shift between the force and the displacement as an image format, and then also the stiffness in an image format. This is for a fiber epoxy composite. You can see immediately the contrast in the image, that the central region is basically a fiber, and then you can see the epoxy region. And once you have this raw data, you can convert that into a storage and loss modulus and in an image format. To do that, for example, this particular image has 256 by 256 points. If you have to do these experiments one indent at a time, it probably take, even if you do it a one indent per minute, it will probably take about 30 to 40 days. Whereas with this mapping technique, you can get this property map within about like 5 to 10 minutes, okay, by not only doing the experiment, but also analyzing the data. So then we have this kind of a powerful way of looking at the data and taking the cross-section at any point. For example, I've given the cross-section image of the storage modulus for this fiber epoxy composite. You can do that for loss and storage modulus. So it's a very powerful technique. You can simply implement on any polymer surface. You do have to have a very nice smooth surface, because roughness may affect your stiffness measurement. And if you have a very nice smooth surface, and if you do it slow enough, like if you take even 5 minutes to do this experiment, you can get a quantitative map of this property very beautifully on a variety of materials. And it is very useful for polymer materials, okay? So now, but in the previous experiment that I have mentioned, it only applicable for only measuring the modulus of the material, because we are making a very light contact, very small force. There is no plastic deformation. So the information that you are getting is the elastic response or the viscoelastic response of the material. It doesn't allow you to get the plastic deformation of the material. But you can do that by doing inundation, but at a very rapid way. Where, for example, like if you can do this inundation for higher depth, where you can induce this plasticity, along with this elastic deformation, if you can also measure the plastic deformation, elastoplastic deformation, then you do it in a very rapid way. For example, if you can do, like, for example, in 1 second, if you can do like 5 or 6 indents, that is pretty fast. And in that way, you can have hundreds of indents, thousands of indents within a minute. and then you can process the unloading curve and get the load displacement response and stiffness, and calculate the hardness and modulus at different grid positions. In that way, you can also construct a map. Okay. To do that, very important thing is that you need to have the right control system, you need to have the right hardware, where it's in, and the system that we use in Hydron or the Bruker system, you have this piezo scanner capable of moving the transducer at very fast rate and also in a very controlled manner. The transducer has the dynamic response that it can do at much faster rate. And then the control system should be able to capable of doing this. So with that all combination, you should be able to do this mapping in a traditional way, measuring the indentation depth response as a function of load and processing the data and calculating the properties as a map. And this can be done with our typical system like a TI-980 or an in situ way inside an SEM. And when you do it inside an SEM, there is an added advantage. For example, if you have EBSD or some other thing, you can kind of correlate the map that you get with the EBSD with the map that you can get with this fast property mapping. Okay. So I mentioned to you how you do this. For example, like in a typical load profile, because we wanted to reduce the amount of time that you wanted to spend in a simple indentation, we do a simple load profile, load and unload very fast. And then you pause for some time at very small load or at zero load. During that pause time, you move the tip from one position to the next position, and you do that continuously, like for example, 6 indents per second. Then you get this load displacement response. So then you take this load displacement curve and use the same Oliver and Ford method of analyzing the unloading curve, and then you can plot this hardness and modulus in a map form. So there are very big advantages of doing this very fast indents. First of all, like for example, because you're doing it at a very fast rate, the amount of time that the tip in contact with the samples is very much reduced. So this is very important when you do high temperature measurement. Sometimes the tip reacts with the sample. When you do it very faster way, you don't allow that kinetic reaction to happen. You can prevent that. Second is because you're doing it very faster rate, the low frequency thermal drift problem won't be coming. But still, like it's very important to understand that you're doing at much faster rate. You're not controlling the strain rate. You're controlling only the loading rate. So you have to mention what rates you're doing and when you publish the result, because material may respond differently for the different loading rate. So the rate response is very important. So it has to be mentioned in your publication when you refer when this kind of measurement is done, what rate of loading that you are doing, because some of this material are strain rate sensitive. So that is one of the disadvantage. We can't control the strain rate, but we can control the loading rate. Okay. So with that, this is a typical example for silicon carbide ceramic matrix. This is kind of an aircraft material. And the important aspect is that we wanted to map the properties at a larger scale as well as smaller scale down to kind of one fiber. This is kind of silicon carbide fiber on a silicon carbide matrix. So to understand how the property changes from the fiber to the matrix interface, we were able to do that. And we were able to do like a number of indents, and not only at room temperature, but we were able to also do that these experiments at higher temperatures. I think in the later part of my talk, I may have one slide showing the measurement response at the higher temperature from like 800 degrees C. Okay, so here you can see is the hardness map at this one small region where you see some kind of a phase, and then the matrix. Here you can see the indent placement. The top part showing the hardness map. You can see a clear kind of the image is, seeing image is pretty much kind of revealing what is happening there. You can see how the hardness is different at different region. The same thing, you can also see the modulus, and you can see at the boundary how the modulus is gradually changing. And you can see that from the color rendering pretty nicely. Okay. Another example, this is done on a DB980. It's a steel, and it's a rolled steel. And I mentioned in that previous slide that you can combine this with the kind of a EBSD map And then, for example, in this case, that there are about 100 by 100, there are about 10,000 indents were done within like 2 or 3 minutes. And this is a 15 micron by 15 micron scan. And the EBSD image of the same region that shows all this color differentiation is basically showing the crystallographic orientation. The black color that what you see is basically corresponding to the marking sites. And if you now compare the harness map below it, you can see that how well it matches with the harness map. You can see that dark regions corresponds to this dark blue region, which has highest harness. So you can directly correlate now with the crystallography or the faces that you see on some of the technique to the harness map. Okay, that's one advantage. Again, this is for another example. This is for a titanium and bulk metallic class, a weld zone, where you can see the top part is the titanium, the bottom part is the bulk metallic glass. And when you do the weld zone, you do develop intermetallic phases at the weld zone, and they have a much higher hardness compared to the both material. And you can nicely see that when you do this mapping technique or across the profile, basically from one material to another material, how the interface is changing, how the modulus and hardness is changing at the interface. Okay. Another example, this is a multi-scale mapping in laser gladding. Okay, when you do the laser glad, basically you have kind of a powder jet, which is a steel powder, and then you melt it with a laser beam, and then you deposit on the steel substrate. Now, if you wanted to understand how the property is changing at the interface, what you do is basically from the glad to the base, what you do is basically you take a typical viscous hardness tester and measure the hardness as a function of distance, and then you get this kind of a line profile. This is how you get very coarse information and the property response. And if you do it in an array format with the micro hardness tester, you probably get kind of an image where you can see the region where you have the hardness variation is kind of a repeatable. And you can also kind of, depending upon the laser step size, you can see these domains pretty clearly. So this is how you can do as an array of indent, but this is still a macro scale, okay? Now, if you go at much smaller scale, you can still with this mapping technique, you can do it. And in this particular case, the last image here, what I'm showing over here is basically the harness map. And this map was constructed by doing experiments with a spacing about 500 nanometers between indents. And the first map that what I'm showing is basically EBSD boundary map. It kind of shows you the high angle boundary, and you can see it in the cladding region have this high angle boundary a lot. And then the EBSD IPF map shows you the crystallographic orientation. Now, if you look at the harness map in comparing with this the boundary map, you can pretty much see how the harness is changing along the grind boundary. We can do the same resolution as you do it for EBSD map. We can do this harness map with this technique. Okay. Another example, this is again a railway welding joint. The first image that I'm showing is an SEM image. And the next one is the EBSD map. And you can the color of the map, it shows the crystallographic orientation. And you can also at the boundary, you can see the dark one, the black ones, basically they're all Martin sites. The next image is the in situ SPM image that you can get with the instrument. And then the next image is basically the harness map. And if you look at in close up, you can see that at the grain boundaries, you have these magnetotic islands. And then if you look at the harness is pretty high at the grain boundaries. Okay. You can also see at different colors in the IPF map, which shows different crystal orientation. You can also see the harness map, which has a different harness depending upon the crystal orientations. Now, instead of measuring this data as a number, now it kind of gives you a feel for how you can see from the EBSD how the crystallography is changing and how the harness is changing in your material. I'm just giving as a tool. I'm not talking too much about the material science because I think it's much useful for me to give you the usefulness of this tool rather than talk too much about this material science. Okay. Again, another one, this is same material. This is for steel welding joint, but I just wanted to compare the way that we do in a typical Vickers harness test. We take in a macro or a micro Vickers harness test, we do this test, and they are like a much higher length scale compared to nano-indentation test. And for example, I've shown here a typical Vickers harness test, which is probably about a couple of microns in size. And within that size of this indent, for a simple one Vickers harness test, you can do a number of small nano harness testing. In this particular case, but I'm able to do about 196 indents within that couple of micron Vickers harness test. In one single Vickers harness test, you measure the average mechanical property, but if you do in the same area a number of nano harness tests, you can still get an average property, but then you get a better tight distribution of the statistic in terms of the average. For example, if I plot the harness measured by an indentation technique over the same area as the Vickers harness test has been done, you can see the red curves are for the Vickers harness test, and then the blue curve is basically is for nano harness test taken over an area and then as an average. It gives you very tight distribution. Even within that tight distribution, if you see a big change in the distribution, you can immediately go back and look at the area, and then you can one point to another point we can see what is the variation harness, and we can have a better understanding on why that statistic, why there is so much of deviation in the statistic, because locally the property of the material is changing so much. So you get a better statistical idea of what you're making measurement when you do this kind of imaging technique. Okay. Again, we were able to, we wanted to know how far we can push this technique, what is the best resolution we can do. We used one of the most sensitive probe that we call X probe. This is basically a MEMS-based device where you can apply a very small forces to the piconewtons, and then with that we can apply very small force and very small displacement, so that we can have the spacing to be reduced between the indents. In this particular case, we were able to reduce to like 100 nanometers between the indents, and then it can map this. This is another example. This is for high entropy alloy, iron aluminum based high entropy alloy. You can see that again, EBSD phase map and the first image showing the distribution of the iron as well as the aluminum. And then you can see the crystallographic orientation in the IPF map of the EBSD. And then if you compare the harness map, it completely gives you the contrast at different regions. This is a high resolution harness map, as good as your EBSD or a phase map that you can get with the EBSD. Okay, so this is very important because now you have a direct comparison correlation, structure property correlation down to this crystallographic scale. Okay. Again, I'm going to go speed it up. You can do these experiments as a function of temperature and using this Excel heating stage. This is the Excel heating stage that we typically use. This stage has been designed to eliminate drift. We can sandwich a sample between this top heater and the bottom heater. And then when they are sandwiched, then you have a gasket. You create a small space between this top and the bottom heater. Within that space, you can control the atmosphere. You can put an inert gas, or you can have, for example, the cold nitrogen or humid air. So you can kind of have different atmosphere, whatever the way you want in that micro chamber. And then you can do the experiment, and you can do this mapping experiment that I just presented. So let's look at for silicon carbide. This is again, like I already presented for room temperature. In silicon carbide matrix material, the fibers are also silicon carbide, the matrix also silicon carbide. I mentioned that we wanted to study as a function of temperature as well as how the property is changing across the interface, that you can see clearly at 400 degrees C as well as 800 degrees C, and the harness and modulus map. Okay. Now, you can also do it at, I mentioned that you can do it at the cryogenic temperature by passing a whole nitrogen. gas into the chamber in the same exhaust setup, and then you can cool it down to minus 120 degrees C. And this is for steel sample, and you can see that in the in situ SPM imaging, you can see the pear-like colonies as well as the ferrites. And with respect to inundation hardness mapping, you can compare that now even at 0 degrees centigrade. Okay. So I'm going to go and show this particular result. For example, you can now do this experiment as a function of temperature from room temperature to very cold temperature up to minus 120 degrees C. And then you can understand the mechanical behavior. For in this case, basically, we can observe the ductile to brittle transition in 1018 steel, whereas this low displacement curves gives you an idea how the deformation is taking place, where you can see that smooth, nice low displacement curve at room temperature. As you reduce the temperature, you started to see these serrations, typically because of the brittle behavior of the material. So you can do this pretty nicely with this low displacement curve analysis in terms of a map or in terms of a single point, and you can observe this ductile brittle transition. Okay. So same thing for a different steel. So I just wanted to quickly give an idea. You can do the same experiments inside a scanning electron microscope, and you can do that XPM analysis. Now it wasn't available a few years ago, but recently we kind of introduced that this functionality inside the SEM. So now we can do these experiments inside the SEM. I can directly go and check that with the EBSD to get the EBSD map. If you have the rotation and tilt stage instead of just the linear stage that I'm showing over here, with the rotation and tilt stage, you can do this indentation experiment, or you can go to the EBSD detector, do the map, bring back to the indenter, and then do the indentation experiment. I'm kind of going to show you a typical indentation experiment done with this high throughput property mapping inside the SEM. You can see that how it is done. Okay, inside the SEM. Just to give an information how this is done. Video is better to, instead of just giving oral presentation. Okay. So with this, I will stop here because I think we are pretty much at the end of this timeline. So I will take any questions from the audience.
Thanks, Dr. Asif. Yep. So yeah, it was pretty good detailed talk going from all the instrumentation. So any questions from the audience, from the participants?
Or I had a quick question, Pratyank.
Yeah, sure. Please go ahead.
Yeah, hi Asif. Thanks for
Hi,
the
Prita. Yeah.
talk. Thanks for waking up in the middle of the night to talk to us.
Yeah.
So Asif, about these, several indents done using, I think, I forget what the instrument is called.
XPM.
XPM. Yeah.
XPM, right?
Yeah.
So what is the? We always worry about these deformed regions interacting with each other and so
That's
on.
right. Yeah.
So people were using it. So are we still able to maintain this roughly 5 times the indent size separation between the indents?
That's true. That's true. The indent spacing is very important because they overlap. For example, even the elastic region overlap over a larger length scale compared to plastic deformation, because plastic deformation is very local. But still, you need to maintain kind of the spacing between the indents. Typically, like for example, if you do 100 nanometer, we keep about 3 or 4 micron spacing. So like what you said, that 5 times in the depth, we try to keep so that's why, like we wanted to do a high density map. Our system is capable of placing even as close as 100 nanometers, but you need to do a very small indent. So that's why I shown that for that you need to use this high sensitive MEMS transducer, so that you apply a very small force. So still keep like 100 nanometer spacing, because the indents in those cases are like maybe about few nanometers.
Right.
Okay. Yeah, you have to keep the distance. That's true.
Okay.
Okay.
Yeah. Thanks.
Okay.
Sure. I think we have no further questions, right?
I was asking a quick question. So about this dynamic indentation, is it still like at higher strain rate? So I knew about one instrument in micromaterials, which basically IMDEA Materials had that. That's basically pendulum impact test. But this
Yeah.
dynamic test is basically a high strain rate test, right?
Yeah, you can do that even with our typical system. I don't have the slide. We can go very high strain rate by slamming the tip into the sample and measuring the high strain rate response. That can be done with this instrument as well. We have recently published a few publications. Very high strain rate, 10^6 can achieve very high strain rate. Yeah.
I see. And you get load
Yep.
versus depth
Displacement. Yeah.
information during that.
Yeah,
Okay.
very high data acquisition rate, like for example, maybe 20,000 data points per second or maybe even more. You can pretty much capture the whole impact and strain rate response.
I see.
Yeah.
Okay. Okay.
Yeah. Okay.
Yeah. Okay. Any further questions? I don't see any further questions from the participants. So I think we conclude the talk. Yeah, then we'll just present the vote of thanks. So on behalf of Indian Institute of Technology, Goa, Bruker and Industron, I would like to thank our all eminent speakers, especially Professor Prita Pant for spending time, Professor Llorca from Spain, Madrid,
Hello, sir.
spending time from their busy schedule, and Professor Dr. Syed Asif for waking up early in the early morning, I would say like 3:30 a.m. from Minneapolis, and joining us to share his experience. At the same time, to have any successful event is good to have a equally, engaged participation from the audience, students, faculty, the research communities. I would like to thank all the participants for joining us today. And I also would like to take the opportunity that we are trying to, make this awareness of such a beautiful technology, which can be really very helpful in understanding the materials properties. So we also have a center in Trivandrum where we do collaborative work. We also have a demo center where we can do contract-based testing. So we are quite open to help our research community in India, whether from industry or academia. So if you guys have any questions, please feel free to reach us. We'll be happy to help you. So at the end, we conclude our session for today. Anybody has any questions, please can reach me at my email IDs, which you probably have received during the registrations. Sure. So stay safe. Yeah. Have a great evening. Yeah, everyone.
Bye.
Okay, bye. Thank you. Thank you, everyone.
Thanks. Thanks. Bye.
Bye. Bye, guys.
Thank you.
Take care.